Thank you, Christopher and Mihail. Nice presentation. Welcome to the talk, Get Started in Minutes with Grafana Mimir. My name is Marco. I'm a software engineer at Grafana Labs, and I'm also a Grafana Mimir maintainer. Today, along with me, there's my colleague and friend, Peter. Peter, would you like to introduce yourself?
Hello, my name is Peter, and like Marco, I'm an engineer at Grafana Labs, and a Grafana Mimir maintainer. Thank you for joining us today.
In this talk, I'm going to give you an introduction to Grafana Mimir, our new open source scalable time series database. And then Peter will show you how to get it started in a few minutes. Now, the three pillars of observability are metrics, logs, and traces. With metrics, you can find what went wrong, and then you can find more details exposed through the logs. Traces go a step further and allows you to have a detailed view on a single request. And you see where in the code or in which service of your distributed system it went wrong. Metrics are the foundation of any observability stack. We see an increasing need for a metric system which is easy to configure and run and can reliably run at any scale, from small projects to large enterprise companies. One of the most common use cases is having a global view across your infrastructure. If you are familiar with Prometheus, the recommended way to run it is to keep it close to the monitored targets. The typical scenario is that you run a Prometheus server in each Kubernetes cluster or cloud region or data center, and then you want an effective way to run any query on all the Prometheus server metrics. For example, how can you query the 99 percentile latency for your application across two different regions? And then what happens when a single Prometheus server is restarted or goes out of memory? If you don't have a highly available setup, you will experience gaps in your metrics, which effectively means you have a blind spot in your observability. Last but not the least, scalability and performance. We see companies with tens to hundreds of millions of metrics, and they need a scalable, reliable, and performant solution to store such very large amount of metrics. You want to run your high cardinality queries faster and have a long retention period for your metrics, so you can analyze your historical data as well. As an example, in Grafana Cloud, we run Mimir with a retention of at least 1 year for any customer. So we recently announced Grafana Mimir, our new open source distributed time series database. Mimir provides high availability, horizontal scalability, multi-tenancy, a durable storage, and fast query performance. Mimir has been designed to be easy to configure and run at any scale, from small lab projects to large companies, having hundreds of millions or even billions of active time series. Now, it's very important to understand that Mimir does not replace Prometheus, but it aims to extend Prometheus. When using Mimir, you keep running Prometheus configured to scrape metrics from your applications and infrastructure, and you configure Prometheus to remote write these metrics to Grafana Mimir. And then you configure Grafana to query the metrics from Mimir, leveraging on Mimir scalability and performance optimizations. Alternatively, instead of using Prometheus, you can also use the Grafana agent or the Prometheus agent to send data directly to Mimir. Both the Grafana agent and the Prometheus agent are open source projects. Now, the advantage of using the Grafana agent relative to Prometheus is that the agent is far more lightweight in terms of CPU, memory, and disk utilization. The agent doesn't store metrics locally, but just push them to Mimir. The agent is also suitable for being deployed on the edge. For example, you can have an agent running on every single machine of your infrastructure. The typical setup is to run a pair of Prometheus servers or Grafana agent per Kubernetes cluster or cloud region or data center. And these Prometheus servers run with the same configuration, they scrape the same metrics from the same targets, and they both remote write these metrics to a centralized Mimir cluster. Mimir then deduplicates the received metrics and exposes a compatible Prometheus API to query. Mimir only requires an object storage. We support AWS S3 or S3 compatible storages like Minayo. We also support Google Cloud Storage, Azure Blob Storage, and OpenStack Swift. Just to give you an example, the Mimir tutorial available in the Mimir repository uses Minayo running in a Docker container to have a quick way to get it up and running without using a storage service offered by a cloud provider. So, related to the challenges I was showing you before, Mimir offers a global view across all your metrics, and it's deployed as a centralized cluster, storing and querying all your metrics. The metrics data is replicated three-way, and the Mimir architecture is horizontally scalable. If you need more capacity on your cluster, just add more replicas. The long-term metrics data is stored in an object storage, which means the cost of the long-term retention is low and the capacity is virtually unlimited. Mimir employs multiple caching layers and some query acceleration techniques like query sharding to offer best-in-class PromQL query performance. Multi-tenancy is natively built into Mimir from day zero, and the tenant's data is isolated in the storage. Mimir also supports per-tenant limits and some advanced techniques like shuffle sharding to ensure a single tenant can't take all the cluster resources and negatively affect other tenants' workload.
Thank you for the introduction, Marco. Mimir uses a microservices architecture. However, you are not forced to deploy every single Mimir component as a separate deployments. You can deploy Grafana Mimir in two different modes, microservices mode and monolithic mode. In microservices mode, the deployment mode follows the Mimir architecture and components are deployed in distinct processes. Scaling is per component. For example, you independently scale the distributor or the ingesters, which allows for great flexibility in scaling and more granular failure domains. The monolithic mode runs all required components in a single process, and then you scale the cluster running multiple processes across different machines. Monolithic mode is the simplest way to deploy and operate Grafana Mimir. Both are production grade. For example, we have customers running monolithic mode at scale. We currently provide three main installation options: Helm charts, JSONet, and binaries. Helm is the easiest way to get Mimir up and running in Kubernetes, and that is what we will use in our demo. JSONet is another option to deploy Mimir in Kubernetes, which is currently more flexible than our Helm charts in terms of supported customizations. Both Helm and JSONet install Mimir in microservices mode. Binaries give you the freedom to run Mimir on any platform and infrastructure using your preferred deployment mode. Binaries are typically used by people who want to deploy outside of Kubernetes or in monolithic mode. In the Mimir repository, you can also find a tutorial for getting started with Mimir quickly, and this tutorial uses Docker Compose setup that does not require Kubernetes. In the following demo, we will see how to deploy Grafana Mimir to a Kubernetes cluster using Helm charts. We will then configure Grafana agent to scrape metrics from Mimir itself and send those metrics back into Mimir. Finally, we will look at how to connect Grafana to Mimir and how to use some existing dashboards to view the state of our Mimir deployment. You can find all used configuration files from the demo in the Mimir GitHub repository in the docs configuration GrafanaCon 2022 directory. During the demo, we will assume that our Helm is configured with Grafana repository of Helm charts. We expect to have a Grafana agent operator running in the Kubernetes cluster. We assume that our Kubernetes cluster supports ingress, and we have an existing Mimir Helm DNS entry pointing to the IP address of the ingress. For the sake of simplicity, we will deploy everything to the default namespace. As a first step, we will run helm install command to install Mimir. Helm uses the concept of releases to distinguish between different installations. Our release will be called gcon for GrafanaCon. In Mimir values YAML file, we configure some options of the Mimir Helm chart. We enable ingress and use Mimir Helm as the hostname. We enable service monitors. This will be used in the next step when we configure Grafana agent to scrape metrics from Mimir. And we also set scraping interval for Mimir metrics to 10 seconds. By default, Grafana agent scrapes metrics every 60 seconds, but operational rules provided by Mimir team assume a lower scrape interval. Mimir requires an object storage to store data. Mimir Helm chart comes pre-configured to use MinIO, which is S3 compatible object store. With Mimir running, we will now configure Grafana agent to scrape metrics from Mimir and send them into Mimir. To do that, we will add metrics instance resources to our Kubernetes cluster. Grafana agent operator looks for metrics instance resources and starts new Grafana agent for each of them. Grafana agent will then use matching service monitors to scrape metrics and forward the metrics to configured remote write endpoint. When we set up Mimir in the previous step, we enabled service monitors. In this step, we let Grafana agent to use all service monitors in the same namespace. Our configuration for Grafana agent needs to specify URL for remote write. Since Grafana agent runs inside Kubernetes server, it cannot use ingress hostname, but we can send metrics directly to Mimir's distributor service. Before continuing our demo with Grafana setup and the Mimir dashboards, let's import rules provided by Mimir team. Some panels in Mimir dashboards will require use of these rules, and without them, we would see some of the panels empty. We will also import alerts. Let's now configure Grafana to access Mimir and check if we can query the data back. Mimir exposes Prometheus-compatible API for querying under /Prometheus prefix. To use this from Grafana, we need to create new Prometheus data source. We will use Mimir Helm as the hostname, the same as used previously to configure our ingress. We now have a data source in Grafana set up. Grafana has also detected the correct type, Mimir. After adding data source, let's verify that we can query Mimir by running a simple query in Explore view. This query checks for the number of Mimir build info metrics, which is exported by each running Mimir pod. We can see 11 of them. Now we are ready to import some Mimir dashboards to monitor the state of our Mimir deployment. We start with Mimir writes dashboard, which shows health metrics for the write path. We can now finally see how Mimir is working. Let's also import Mimir reads dashboard, which is similar to Mimir writes, but shows health of the read path instead. Oops. We haven't sent many queries or read requests to our Mimir instance yet, but all queries from Grafana to show our panels contribute to the stats of this dashboard. You can now also manage your Mimir rules and alerts via alerting support in Grafana. In this view, you can see all installed rule groups and their state. You can also create new rules and alerts or explore and modify the expressions. Mimir includes a rich set of production-grade Grafana dashboards and Prometheus alerts, which you can use to monitor Mimir itself. Dashboards both give you an overview of the health and traffic on the system and allow you to drill down into performance and insights about potential issues. For each alert, we also provide a detailed playbook how to investigate and fix the issue. This is the same set of dashboards, alerts, and playbooks that we use internally to run Mimir in Grafana Cloud. We recommend to use them when running Mimir in production. In this demo, we started Mimir by using a simple but scalable deployment. We have three main suggestions to get the best performance out of Mimir. Cache everything. Mimir makes an extensive use of caching backed by Memcached. Enabling caching will improve your query performance by orders of magnitude. Enable query sharding. Make sure that query sharding is enabled in your configuration. With query sharding, a single query execution will be distributed across multiple machines, and it will significantly improve your query performance. Finally, if you have tenants with more than 20 million active series, make sure to fine-tune the number of compactor shards for the tenant. The rule of thumb we suggest is 1 shard for every 20 million active series. You can find more production tips at the link on the screen.
Thanks, Peter. Nice demo. In this last part of the talk, I would like to give you a quick look to the future of the project. Now, there's a lot going on in the Mimir project. We continuously work to make it more scalable, performant, and easier to operate. Just to give you an example, there's a huge ongoing work to further simplify Mimir installation, configuration, and operability. However, in the next few slides, I would like to highlight some of the biggest features we are currently working on. First of all, we want to make Mimir a general-purpose time series database. We want to be able to ingest your metrics, whatever system you're using. We are currently working to add OpenTelemetry, Graphite, Influx, and Datadog metrics ingestion support in Mimir. This will happen in the following releases. Also, similarly to Prometheus, we currently have two main limitations on the write path. Mimir cannot ingest data points older than 1 hour compared to the most recent data point received. And also, Mimir cannot ingest data points out of order for a given metric. This means any data point we receive must have a timestamp which is newer compared to the previous one for the same metric. We are currently working to ingest samples with any timestamp in any order. We plan to have an experimental support in a few months and a stable version by the end of the year. We are also seeing a lot of demand to ease the migration of metrics data from other systems to Mimir. We are currently working on a backfill API and a command line tool which allows you to easily migrate your metrics data from Prometheus and other systems to Mimir. To sum up, Mimir is a multi-tenant, highly available, horizontally scalable time series database. It has been designed to be easy to use, scale out quickly, and offer best-in-class performance. On the right side of the screen, you can find the link to the Grafana Mimir repository and documentation. Let me also remind you that Grafana Enterprise Metrics is built on top of Mimir and adds some extra features like fine-grained access control or cross-cluster query federation. And also, we offer a commercial support. Finally, you can also get all of these out of the box, just signing up on Grafana Cloud. We have a free plan that you can use to start using Mimir but also Loki for logs and Tempo for traces, managed in the cloud in just a couple of clicks. If you want, you can also join the Mimir Slack channel in the Grafana Labs community workspace, where you can ask questions and engage with the Mimir maintainers and the community. The presentation is over, and we are now going to have a Q&A session.
All right, hello everyone. Marco and Peter here, and my name is Jen Pia. I'm going to be help moderating the Q&A session. I'm a product manager on the Mimir team. So we got a lot of great questions here, so I'm just going to jump right into it. And the first one here is going to be for Marco. So can you talk about how Mimir is different from Thanos? And then do you have any performance comparisons between Mimir and Thanos?
Right. Sure. Well, Thanos is a great piece of software, and the Thanos team has done a great job building, a vibrant community. I literally love and respect Thanos a lot. The Mimir storage engine has been inspired by Thanos, and we also reuse some part of the code. Now, Mimir makes it even more scalable and performant. We added features to scale it further, like the new scalable compactor or the query sharding engine. Mimir is also multi-tenant since day zero, and the different tenants data is isolated in the storage. We also support features like shuffle sharding for better isolations between different tenants. We have plenty of per tenant limits in place to ensure that one single tenant can't take down the entire cluster or even affect other tenants' performances. You also mentioned if we provide any performance comparison. We typically recommend users and also our customers to run comparison by themselves. We don't want to provide a comparison based on synthetic data. We prefer you run your own queries on your own data. If you want to run benchmarks in the Mimir repo, you can also find a K6 script. K6 is a Grafana Labs load testing tool to load test both systems. You set up Thanos, you set up Mimir, you load test both of them, writing the same data, query back the same data, and then you can compare the performances based on your use case, based on your installation, running on your infrastructure with your own object storage, and so on.
All right, thanks, Marco. Next question here is for Peter. So Peter, can you help folks understand? They want to know what format Mimir stores data in object storage.
So that's easy one because Mimir is actually using the same format as Prometheus and Thanos.
Marco, are you getting it? I have some Peter, your mic is a little bit.
Yeah, there's an issue with your microphone, Peter, I think.
Peter, if you could just refresh the browser and I'll bring you back in.
Okay.
I can take this question in the meanwhile.
Sure, yeah.
Quoting what Peter was trying to say, we use the Prometheus TSDB format. So basically, we use the same data format on disk as Prometheus and as Thanos as well. Following up the previous question. So this makes very easy to migrate from Prometheus to Mimir, or eventually from Thanos to Mimir, and eventually even back if you want, given the storage is compatible between these projects.
Great. All right, Peter, let's try it again. And sending the next one your way. Does Mimir support native compression? And if so, what sort of compression can users anticipate?
So as we said previously, I hope you can hear me now, we are using TSDB format. And in TSDB format, usually one sample, which is one timestamp plus one sample in float64 format, would normally, without any compression, take 16 bytes. However, TSDB compresses that, and on average, one sample takes 1.3 bytes. So that's the compression that we provide.
All right. Another kind of related storage question that I see came in here. Is there any sort of concept of hot or warm? I imagine this is related to storage, but hot or warm storage in Mimir. Marco, you want to take this one?
Yeah, sure. So the most recent data is stored and queried from the Mimir ingesters. If you run Mimir with the default configuration, the last 12 hours of matrix data are queried just from the ingesters. So from this perspective, ingesters are our hot storage. All their data is stored on the object storage, like AWS S3 or Google Cloud Storage, Azure Blob Storage, as mentioned during the presentation as well. And they are queried through a Mimir component, which is called the store gateway. The data, the TSDB blocks are never fully downloaded on disk. We just fetch the relative portions of the blocks directly from the object storage, running get byte range requests in order to satisfy the query. From this perspective, I think could say that object storage usage of Mimir is a sort of warm storage.
Awesome. Question for you here, Peter, and maybe this is something we can clarify for the person that asked the question. So the original question was, is it recommended best practice to separate Loki and Prometheus data as different tenants in Mimir? So maybe you can clarify there with Loki being kind of a separate system, but maybe just go over kind of how you think about how you create tenants in Mimir and like what that tends to map to in the user's organization.
Mm-hmm. So both Loki and Mimir use the block storage to store their data. And I would not recommend mixing the two systems to use the same block storage or the same bucket. Because Mimir will actually try to scan for all the tenants, which means top-level directories in the bucket, and will interpret any such directory as a tenant name. And will even try to run some maintenance over such users. So if you store the Loki data in the same bucket, Mimir will try to actively scan what's inside the data and will try to maintain the content of it. However, we have recently introduced a new feature where you can configure Mimir with a specific prefix which can be used in the bucket. So using this feature, you might be able to mix the Loki and Mimir data. However, I would still recommend different buckets for this setup.
Okay. Maybe to bring us home here, Marco, last question. Are there any tools to assist with migrating from Prometheus to Mimir?
Yeah, sure. Maybe Peter is better to answer this question since you work on that.
So we have a Mimir tool. We have a meta convert tool which is able to modify the metadata of blocks that you manually put into your bucket. However, we are currently working on a backfilling API, which will also be supported by Mimir tool, which will allow you to upload existing blocks from your Prometheus or Thanos into Mimir bucket.
Peter, what's about if you want to migrate from Cortex to Mimir?
You need to manually copy your data and run meta convert at the moment. In the future, we will have this backfill API, and Mimir tool will support the API natively.
And then maybe just one thing I wanted to add there is, what Peter and Marco touched on was about kind of historic backfill of data. But if you're running Prometheus today and you don't necessarily care about importing that historic data, there's nothing stopping you from just setting up Mimir and starting to point your remote right at it. And there's no actual migration that's required. I think we are at time here. So thanks everyone. Sorry we didn't get to all the questions, but please come find us on the community channel, on our GitHub page. We're excited to keep growing the project. So thanks.
Thank you all.
Thank you very much.